Hey everybody! Oh my gosh, I am so sorry. I am so late. I totally forgot about doing review. So this is Mrs. Mancuso and we are reviewing chemistry, and this is for the 35-week test. All right, so in the comment section, I want you to write down what you want me to review. What would you like to go over together? All right, so this right away is making me think of a word in chemistry. And the word in chemistry that I'm thinking of right now is entropy, because entropy means the state of disorder. It's telling you how much disorder is going on in your system. So right now, a lot of entropy, a lot of disorder. So if we think of chemistry disorder, the most disorder is a gas. So that has the highest entropy, because you can picture the molecules are all over the place and they're spread out. So there's a lot of disorder. And on the other end, with very low entropy, would be a solid, because the molecules are all organized in a nice geometric shape. So this is one way of looking at entropy. So entropy will decrease as you go from a gas to a solid, or entropy will increase as you melt it and boil it and go from a solid to a liquid to a gas. All right, another thing about entropy is if you have a compound, like let's say you have water, and you're going to break it down into the elements H2 and O2. Well, you are definitely going to increase the amount of entropy, because this is a compound. This is organized and together, and it would require a lot of energy to change it into these gas molecules. You would have to do this with an electrolytic cell. So I'll go into electrolytic cells and we'll talk about splitting water. So here can be my electrolytic cells, and here are my two electrodes, and we'll say this is the positive and this is the negative, and it has to get hooked up to a battery. So again, hi guys, I'm seeing all the little comments. Hi peeps, I know everyone loves chem. Love you all. All right, so here is an electrolytic cell. An electrolytic cell means that it is a non-spontaneous reaction, which means you need energy in order for this reaction to happen. And there's my energy source, that battery right there. So that battery is what is allowing my reaction to occur. Now, if my reaction is splitting water, I have H2O. Actually, I just wrote the reaction right here, so I'll keep it right there. I have H2O forming H2 and O2, and the first thing I want to do is balance out this reaction. I know I have H2 and O2 because these are both diatomic elements. So to balance that out, two O's, so I put a 2 in front of this. Now I have two O's, but now I have four H's. So to balance that out, I put a 2 there. All right, oxidation states. Here, hydrogen's a +1 and oxygen is a -2. Hydrogen is a 0 because it is alone, and oxygen is a 0 because it's alone. So I can now think about what is being oxidized and what is being reduced. My H is going from a +1 down to a 0, so my H is being reduced, and my oxygen is going from a -2 up to a 0, so this is being oxidized. Yeah, I can definitely go over sig figs, Dan. I know you are not in chemistry, but you know I love sig figs, so I'd be happy to do that. All right, so let's talk about where redox occurs. So reduction always happens at the cathode, and if there is a battery, my cathode is negative. So this is my cathode, or my red cat, and over here is my anox, anode, oxidation. And so this positive charge, this oxidation, is going to attract my O's right here. So O -2 is going to go here, and my H pluses are going to go here. So if I write my half reactions, sorry, I need another piece of paper to do this. So if I write my half reactions, I have two O's at -2 become O2. all right? It's changing from a -2 down to a 0, so that's a change of 2 times 2 atoms, so it's losing 4 electrons. And remember that every time you have oxidation, oxidation is losing, and my oxidation number is going up. Reduction is gaining electrons. Reduction is gaining. And then my oxidation number goes down. So I like to have this saying, oil rig. The oil goes up out of the earth when the rig goes down. And so that helps you remember it, I think. It's just a little easy trick to remember it. And now to write my reduction half reaction, I have 2 H2s at +1, plus I'm going to add electrons before the arrow because reduction is gaining, and it forms, if I pull this back down here, 2 H2s at 0. 2 H2s at 0. All right, I changed by 1, and 2 times 2 is 4 atoms. 1 times 4 is 4 electrons. So to figure out the number of electrons, you always do the change in charge times the number of atoms. And if I balance my reaction, these should come out equal, and they do. So again, this was a redox reaction. It was, in order to answer some of your questions, it is not spontaneous because it has a battery. If there was no battery and the reaction did occur, it would be spontaneous. So the question, what if it's spontaneous, or could it be spontaneous without a battery? Nope. If you have a battery connected, it's going to be non-spontaneous, always. Now, a voltaic cell is always spontaneous. It never has a battery. So let's do a voltaic cell right now. So a voltaic cell is another electrochemical cell. This one has 2 half cells, and it's joined by a salt bridge, and this is where ions get transferred back and forth. You have 2 electrodes, and your electrodes are connected by a wire. And let's say this one is iron and this one is zinc. Now, I know that this is a voltaic cell, so I know that it's spontaneous. I also know that the conversion is it's going to convert chemical energy. So by doing a chemical reaction, it's going to make electrical energy. Whereas back over here, my electrolytic cell that was non-spontaneous, that used electrical energy to do a chemical reaction. So it converted electrical energy to chemical energy. All right, so if I go back to this, I know that the first things I have to do is figure out where's my anode, where's my cathode, and so I need my reference tables. So I need table J, and on table J, I need to look up iron and zinc. So I look on here, there's zinc. There's iron. So zinc is higher. Whichever one is higher is more active. So that means this is going to be my anox. This is where oxidation is going to occur. And then over here, this one's going to be my red cat. Oxidation is losing electrons, so I show the electrons going through the wire away from the anode to the cathode. Normally, an anode is negative and a cathode is positive. We only did the opposite charges on our electrolytic cell because we had a battery. And so this is negative and this is positive. Now, an anode, the site of oxidation, is going to fall apart. It's going to lose mass. These atoms are going to form ions. So zinc forms Zn plus 2 ions. So I would have Zn plus 2 ions over here. And if I wanted to write my oxidation half reaction, which of course I want to write it, Zn becomes Zn plus 2 plus 2 electrons would be lost. Now over here, iron has 2 different oxidation states, so they would have to tell you the solution. So let's say the solution is FeCl3. That tells me that the ions in here are iron plus 3 ions. So on the red cat side, I always like to say my red cat gets fat. These ions are going to form atoms, making the mass of the cathode increase because this is forming atoms out of ions. To write the reaction, I follow my arrows. So Fe plus 3 plus electrons, because reduction is always gaining electrons, becomes Fe. To go from a 3 to a 0, I would need 3 electrons. All right, these are not balanced. So if I had to do a balanced skeleton reaction, I got to come up with a common number between these two reactions. So I'm going to go with 6 electrons. So if you just have to write half reactions, it is fine to write it just like this. And if instead you need to do a balanced skeleton reaction, this is where you have to do the 6. So to get this side to go to 6 electrons, I have to triple everything. So 3Zn makes 3Zn plus 2 plus 6 electrons. To have this one go to 6, I have to double everything. So 2 Fe plus 3s plus 6 electrons make 2 Fes. My balanced skeleton reaction, I just put it together. 3Zn plus 2 Fe plus 3s becomes 3Zn plus 2 plus 2 Fes. All right, so that would be my balanced skeleton reaction. Again, this is part of the redox unit. This is a voltaic cell. It is spontaneous reaction. I looked up which one was higher to figure out my anode where oxidation would occur because it's a more active metal. And the one that is lower, I labeled my red cat and I wrote out my reactions. All right, so I need you guys to give me some topics. When there is a fork in the reaction, is it oxidation or reduction? All right, so let's do a plating example. That's what you mean by a fork. So if this is, this could be like gold. Let's say I wanted to plate my fork in gold. Okay, I totally can't draw. Here's my fork. Oh, goodness gracious, it looks like a pitchfork. All right, so here we go. Here's my battery. This is definitely an electrolytic cell. The fork is always, or whatever you are plating, is always going to be your red cat. Now, the way that is easy to remember, you are trying to coat this. That means you are trying to make it fat. You're trying to add atoms to it. You're going to have the arrow going this way. So that means this has to be the site of reduction. You want your gold to fall apart and make the atoms form into ions. So we're going to say these are Au plus 1 ions. So this is your anox, and that side is your red cat. Because I have a battery, my oxidation anode is going to be positive, and my cathode is going to be negative. So I can follow it back and do the charges. I can also show that electrons would move this way. Oxidation loses electrons. Reduction gains the electrons. Now, to write the half reactions, Au becomes Au plus 1 electron would be lost. And to write what's happening over here on this side, Au plus 1 plus the 1 electron coming through the wire makes gold. And the gold atoms are going to coat my fork. All right, so that's how you do a plating reaction. All right, I do not have a calculator with me, but I still want to do some sig figs. So let's say I have the number 30,000. That actually only has one sig fig because I'm only confident in that one number. But if I go putting a decimal here, that means I have exactly 30,000. So now I have 5 sig figs. So let's say I am solving for density. Density is equal to mass over volume. Let's say the mass of what I have is 24.3 grams, and it takes up 0.086 milliliters. All right. This has 3 sig figs in it. This has only 2 sig figs in it. That means I want my answer to have only 2 sig figs. So, again, I don't have a calculator. Of course, I'm downstairs, so I don't bug my family. Oh my gosh. Okay. I just found one. Does it work? Not really. Shoot. Of course, this is the only little crapola one I can find. Let's see what I can get. Oh, clear, 24.3. I can't see these numbers enough to do it. All right, but I would have to round my answer so that my answer only had 2 sig figs. Okay, I am 0 for 2 on the calculator. So I guess I'm giving up on sig figs. Give me another topic. All right, people, tell me what you want to go over. Ooh, can I go over endothermic and exothermic? I would love to. So I'm going to make a little T-chart like this. Endothermic, exothermic. So these are both types of reactions. Endothermic reactions require heat, and these ones release heat. And sometimes instead of require, they use the word absorb, but of course that means the same thing. So an endothermic reaction has a heat of the reaction that is positive. That means heat has to go in. And over here, an exothermic reaction has a delta H that's negative. That means that heat is going out of the reaction. If you write the reaction, so I have to go over to table I, here's table I, shows me all of my reactions that would ever be on a Regents exam. And then over here are the delta H's. So this is exothermic, 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 endothermic. These are my reactions. So I'm going to take one that's endothermic, N2 plus O2 makes 2 NOs. And this reaction has a delta H equal to positive 182.6. So if it's endothermic, I need to put the plus 182.6 kilojoules on this side. It has to be before the arrow. Now, if I do a potential energy diagram, I need to start off with a reactant that doesn't have much energy, add in that energy, and then there is my product. So to label this, here is the energy of my reactant. From this line up to the top, that is called my activation energy. From here to here, this is the energy of my products. And the difference between where I start and where I end, that is my delta H. That is the heat of my reaction. It's always equal to P minus R. So that is why this value would come out positive. My product definitely has more energy than my reactants. So this is an endothermic reaction. All right, over here on the exothermic side, I'll just take this very first reaction. CH4 plus 2O2 makes CO2 and 2 H2Os. The delta H on this reaction, or the heat of the reaction, is negative 890.4 kilojoules. So where do I put it? Over here on this side. I am making 890.4 kilojoules by this reaction. And so some people say, wait, it's negative. Why are you putting a positive here? Well, when you write a reaction, you can't write a minus. So over here, it'd be like, oh, this and this minus this heat. So instead, you just say, oh, I'm producing it. So put it on the product side. So that's why I put it over here. All right, when I draw this reaction, I want it to be exothermic. So I start off with a reactant that has a lot of energy. I still put a little bit of energy in, but this is like, woo, down the hill. If you think of these two reactions as you are on a bike, you got to put in a lot of energy to go up the hill. So endothermic reactions go, woo, way up the hill. And then exothermic reactions, woo, way down the hill. If I add the woo, it's so much better, right? Exothermic, releasing energy down the hill. I always start with my reactants. So there's my reactants. And then way over here, here's my energy of the products. So delta H is going to be the difference between them. And P minus R is definitely going to come out with a negative value because you got a tiny number minus a larger number, so that's why it's negative. And then over here, the difference between here and here, that's my activation energy. So your activation energy, how much you need to get it started. All right, one last thing that I want to do, let me just grab another pen or pencil so you can see it a different color. So here's a pencil. If you had to show the effect of a catalyst, you got to start at the exact same spot, go up the exact same angle, but then go down and finish sooner. So this reduces your activation energy. Every time you add a catalyst, you lower the activation energy required for a reaction to occur. All right, I see some more questions, so let me get to those. One is, can you go over Q equals MC delta T on table T? Yeah, so anytime you're talking about Q, Q is equal to heat. So if I want to know how much heat first of all, I want you to remember this graph, like this. All right, so this is what's called a heating curve. So here I started off with a solid. This value would be the melting point. And so what's going on right here is a fusion change. It's going from a solid to a liquid. And then up here, this would be the boiling point, and this is vaporization, and now I have a gas. So if I want to figure out how much heat at any point on here, I have three formulas. Q equals MC delta T, Q equals MHF, and Q equals MHV. So I use this Q equals MC delta T here, here, and here. Any part where I am changing temperature, over here is temperature. So temperature is a reading of kinetic energy. So anytime I'm changing the kinetic energy, I'm changing the temperature. So that's when I use that part of the formula. HF, let me go like this, so I'm not always doing my arrows overlapping. Heat of fusion is right here. If you're changing from a solid to a liquid or a liquid to a solid, that's your heat of fusion. And heat of vaporization is right here. So keywords if you are boiling or condensing. So let's just do an example. Let's say I have 65 grams of water, and I want to heat it from 70 to 85 degrees Celsius. So 70 to 85 degrees Celsius is in here. It's not yet at the boiling point, so I'm definitely on this slope. So I go Q equals MC delta T. My mass is 65. C is specific heat, and I need to go over here. On the front of your reference tables, heat of fusion is 334. Heat of vaporization is 2260. And specific heat, which is C, is 4.18. So I multiply that by 4.18. And then the change in temperature to go from 70 to 85, you are changing it by 15. If I had a calculator, I would multiply those three numbers together, and my answer is in joules. Okay, as long as I have this up, let's also talk about anytime you are changing the temperature, you are changing the kinetic energy. So if I am heating something, my kinetic energy is increasing here, here, and here. When the temperature goes up, the kinetic energy goes up, but the potential energy stays the same. Now, when you are at the plateaus, here and here, both of these spots, the kinetic energy stays the same because the temperature isn't changing. But your potential, since you are adding heat to it, your potential energy is going to be increasing at those points. All right, another question that I got was, can I go over polar and nonpolar? Absolutely. When we are talking about covalent bonding, we are talking about sharing electrons, and it's always between non-metals. So if I think of something covalent, I could think of water. So water is H2O, and if you drew the Lewis dot diagram, oxygen has 6 valence electrons, and then I would have a hydrogen here and a hydrogen here. So you see this sharing of electrons and this sharing of electrons. So if I want to know the polarity, there's two things I can look at: the polarity of the bond or the polarity of the molecule. And these are not the same. The bond is referring to right here, between the O and the H. Is there a pull or is there no pull? So to do this, I need to look up the electronegativity differences. So what I do is I grab my reference table, and you go to table S, the table after the periodic table, and I'm going to look up O's electronegativity, and it's 3.4. And I look up H's electronegativity, and it's 2.2, and I subtract. So that gives me 1.2. Anything that is 0.5 or higher is going to be polar. So this is definitely a polar bond, meaning there is not an equal electronegativity. Oxygen has way more attraction for the electrons, so they're really being pulled to the oxygen side. That makes the O side seem a little bit negative and the H's seem a little bit positive. All right, for the molecule, I am looking for symmetry, and I am looking to see if it is even or uneven distribution of charge. And there's two options. If it's symmetrical with an even, it's going to be nonpolar. If it is asymmetrical and it has an uneven distribution of charge, it's going to be polar. Well, I already showed the uneven distribution of charge. There are electrons that are unshared pairs right here, so that tells me that it's uneven. It's also asymmetrical. I have a hydrogen off to the left and a hydrogen down. So this is definitely a polar molecule with polar bonds. So let me show you a molecule that is nonpolar. HH. Hydrogen gas. A hydrogen with a hydrogen, I don't have to even look up the electronegativity difference because it's going to be 0. This has the same strength as this, so there is no pull between them. It is also symmetrical, so it is definitely a nonpolar molecule with a nonpolar bond. All right, what else do you want me to go over, people? Can you do empirical and molecular formula? Absolutely, I would love to. So, a molecular formula is what is in the actual molecule. So I'm going to use a molecule that you definitely know. That's glucose. And so this is the molecular formula. The molecular formula shows you all of the atoms in the molecule. So this has 24 atoms in the whole molecule. But if you have something really big, it's much easier to look at an empirical formula. So an empirical formula is reduced. So if I want to reduce this, I think about what number could I divide them each by. So I could divide them each by 6. So it would be CH2O. That is the reduced formula of this. So that's how you get an empirical formula. Now, here is another problem that comes up with molecular formulas and empirical formulas. Sometimes they tell you, and I wish I had a calculator right here so that I could do this a little bit easier. Let's see. I'm trying to think if I could do one quickly without a calculator. Well, let me just show you. They'll say, oh, the molecular mass is like 180. I remember one of the problems being like 180. So let's say it's 180 grams, but the empirical formula is CH2O. And so I want to know what's the molecular formula. So what you do is you take 180 and you divide it by the gram formula mass of CH2O. So a C I know is 12.0. H's are 1 each, so that's 2.0. And oxygen is 16. So 12, 13, 14, 40. So this is 40.0. So how many times does 40? Of course, I have to pick something that doesn't evenly go into it. So let's just, let's make this 160 because that'll work. All right, sorry, I don't have a program or a calculator or a thing or a calculator. So if I have 160 divided by 40, this goes into it 4 times. So what that tells me is my empirical formula got reduced by 4. So I'm now going to do 4 times CH2O. So my answer, my molecular formula, would be C4, multiply it by 4, H, 4 times 2 is 8, O4. All right? So that's how you do it. You take the molecular mass, divide it by the gram formula mass. The number you get, you multiply by the empirical formula, and you will get the molecular formula. All right, what else would you like? I have my chem final for college soon. Oh my gosh, Tushy. Oh, okay. People, if you do not know this, I have a YouTube channel. So just search Nancy Mancuso. When you search Nancy Mancuso, you will see Merm. You will see my face. On my YouTube channel, go to playlists. Under playlists, there are lots of things. There's AP Bio, there's all sorts of stuff. But there are chemistry review videos. All right, so watch that. Chemistry review videos. Most of them are less than 10 minutes long, and they are topic by topic by topic. So please, Trishy, hopefully you are seeing this. Hopefully you're not gone yet. I have a lot of review videos on my playlist. You could just watch the ones you need. So like if you need help on just acids and bases or molecular formulas or redox or organic or whatever it is, you can just watch the videos that you need. So go to YouTube. Go to Nancy Mancuso, go to playlists, go to chem review videos. All right, any other topics you guys want me to go over? Anything for tomorrow's test? You know what? I'm going to do a little bit of organic because that is also one of the new topics. So that means there's more questions about organic. So I'm going to make some crazy molecule. All right, is that crazy enough? All right, I got all this stuff going on. So first thing you always have to do, step 1 is always find the longest chain. Oh, let's make it a little more exciting and put a double bond in here too. All right, so here is my molecule, and the first thing I do is I find my longest chain. So there's my longest chain, and I count it up. 1, 2, 3, 4, 5, 6, 7. So I count any other way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5. Definitely 7 is my longest. So now I look up 7, and 7 is hept. There's a double bond, so I call it heptene. And now I have to count my carbons because I have to show where that double bond is. So you always count closest to the action. So this is my action, this and this branch and this branch and this branch. So I am going to start circling my branches so I don't leave them off. So I have 4 branches here. I really want to make up a crazy one. All right, so I'm going to count carbon 1, carbon 2, 3, 4, 5, 6, 7. All right, so the name, the last name of this molecule is 2-heptene because the double bond comes after the second carbon. Now, I have 3 chains that are exactly the same. So one is coming off of carbon 3, one is coming off of carbon 4, and one is coming off of carbon 5. So 3, 4, 5. Tri, because I have 3 of them. Methyl, because each branch only has 1 carbon. So 3, 4, 5, trimethyl. And then off of carbon 4, I have a 2 carbon branch, so that's ethyl. So the name of this molecule would be 3, 4, 5, trimethyl, 4-ethyl, 2-heptene. This is not part of the name. That was just me counting how many carbons were in the longest chain. All right. Now, this has a double bond. So anytime you have a double bond, you have an alkene, and alkenes have the general formula CnH2n. So we're going to test this out and see if it's right. So Cn, so my carbons, 1, 2, 3, 4, 5, 6, 7 in my chain, 8, 9, 10, 11, 12. So C12, so I should have 24 H's. So if you have to draw something, do this first so that you'll be able to check your work. 1, 2, 3. I'm always trying to fill 4 bonds. This carbon already has 1, 2, 3, so I just give it 1 H. So I have 1, 2, 3, 4. This one doesn't get any. 5, 6, 7, 8, 9, 10, 11, 12. This one doesn't need any. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There it is, C12, H24. Every time you put on the H's, you are always fulfilling the rule of 4 bonds. So for example, this carbon, 1, 2, 3, 4. This carbon, 1, 2, 3, 4. This is coming off of carbon 5. That is not connected right there. All right. Anything else you guys want to go over? Give me a topic and I would be happy to review it with you. I'll also post this video. I'll share it. I'll keep it on my story. It stays for 24 hours, but I'll also put it on here so that if you want to look over it at another time, you can. Do you remember what a precipitate is? A precipitate is an insoluble compound, and it forms from a reaction. So let's say I have AgNO3 plus, let's see, I got to make sure I have something soluble at the start. So I got to go over here to table F. All right, here's my table F with all my different compounds. So I am going to say that it is with CaCl2. So here's my reaction, and both of these are soluble. And what I'm going to do is a double replacement reaction. So Ag is going to go with Cl. Ca is going to go with NO3. I'm going to crisscross. So I'm going to put the charges on top of them like that. And then I go, all right, Ag is a +1, Cl is a -1. So one of my products is going to be AgCl. My other product, Ca is a +2, NO3 is a -1, crisscross. My other product is Ca, NO3, 2 of them. All right, so there's my reaction. And now one of these is a precipitate. So I go on table F, and I notice right away that NO3 right here is always soluble. So that is soluble. But this one right here, AgCl, when you have Cl, it is soluble unless you put it with Ag. So this right here, that's going to be my precipitate. That is my insoluble product. And sometimes a question will say like, hey, why does this reaction go to completion? That means like it does not go reversible. It just ends. And one of the reasons why this reaction would end is because it forms a precipitate. Another way that I've seen that question, why does a reaction go to completion? If you have a reaction that's happening here in a beaker and one of your products is a gas, well, that gas is going to escape unless you have a cover on it. So if you do not have a cover, your gas will escape. And if your gas escapes, then you are done with your reaction and you cannot have a reversible reaction. All right, you guys got to give me some more topics. I'm not sure what else you want to go over. So again, if you didn't see it before, I do have a YouTube channel. It's a perfect time of year to be reviewing. Obviously, MERM, my name is Nancy Mancuso. You'll see my face. Go to playlists. There's chem review videos. Oh, I didn't say this. This is good for end of year. I also go over exams. So it's called Regents. And Regents Review. So if you go in the Regents Review playlist, that has Regents exams, and it has me actually taking the exams. So you can see like question by question how I solve everything. So you might want to go to some of these tonight if you're prepping for your 35-week test. That might help you get ready for your test. But if there's something else that you want me to go over, I would be happy to. You just got to give me a topic, put it in the comments, and I will go over it. And if nobody gives me a topic, I'm going to stop. Anyone have a topic for me? Something you want me to go over? All right, MERM is peacing out. Have a great night. Do well on your test and go watch some of those videos. Get some extra help. Bye.